Welcome back, everybody. So now I want to look at another application of transfinite recursion theorem, and this application is going to lead us into our last, well, not the last, the one before last axiom in our list, the replacement axiom. So here is the idea that I want to go through. So consider this, it's a well ordering, omega plus omega. I was calling it before natural numbers plus the natural numbers. I'm going to draw here what it looks like. It has a first element that we call 0, and another element that we call 1, and another element that we call 2, another element that we call 3, dot on, and then it starts like omega. And then, after all these elements comes another element that we call omega. And notice omega is actually equal, like the elements below omega are actually equal to omega. And then comes another one that we're going to call omega plus 1, and then comes another one that we're going to call omega plus 2, and omega plus 3, omega plus 4, and this goes on. And here we have like another copy of omega. Alright, so that's how this guy here looks like. So now we want to do the following. We want to define the extensions of this. Remember the V0, V1, V2 that we had at the beginning of the class? We started with V0 being the empty set and the power set and the power set, and we would iterate the power set and consider all this and build this finite set of finite sets of finite sets of finite sets. Remember that part? So we want to extend this now not only on the finite sets, like finite levels, but go to omega plus omega levels. So let's first review what that was. If you remember, so V0 was the empty set, and V1 was the power set of the empty set, which is just that. V2 was the power set of the power set of the empty set, which contained the empty set and the set with the empty set. And so on and so forth, and we got Vn plus 1 was the power set of Vn, right? Which essentially contains all the sets that you can write. I've been with brackets and empty sets of kind of depth n. And then we kept on going. And then, I don't know if you remember, we defined at some point V omega to be the union of all these Vn's for n in omega. Right? You guys remember this? If you notice, it happens if you start with the empty set. If you start with something else, it's not true, but if you start with the empty set, you get that V0 is a subset of V1, well, just because the empty set is a subset of everything. And then if you have something a subset of something and you take power sets, this preserves being a subset. This preserves being a subset. So we actually get a chain of bigger and bigger subsets, and then here we get the union. Okay, so actually Vn plus 1 is not only equals to Vn, it's also equal to power set of V0 union power set of V1 union power set of Vn. This is kind of trivial, and what I'm saying here is because, well, they are all included in each other, and the last one is the biggest one. So the last one is when you take the union of a nested chain, you just get the biggest one, right? Because they are all included in each other. So this is very trivial, but I just want to put this in the format of this definition here, right? So this is exactly the union of power set of Vi for I less than n plus 1, which is what we are defining right here. This is just this is exactly the union of the power set of Vi for I less than n plus 1, which is exactly what we are defining right here, right? And then that has the form that we want up there, right? And then this one is the union of the power set of Vi for I less than omega. Correct? So that's what we have up there. So what comes next? Let's see what comes next. Well, then comes v omega plus 1, and it's going to be essentially the power set of this guy, right? Well, it's going to be, if you follow the definition, it's going to be the union of the power set of all these previous guys, right? It's the union of the power sets of all the previous guys, but the union of the power sets of these guys is already this one, which is transitive. So we are actually going to get right here, if you apply the definition, the power set of v omega. Okay, so we get the power set of v0 union the power set of v1 union all the way, and then you get the power set of the last one, v omega, and again they are all nested including each other, so you end up with the power set of v omega. And then again, since they are nested, v omega plus 2, you get the power set of the power set of v omega. And so on and so forth. Right? Then you get essentially v omega plus n is n iterations of the power set. Okay, so question for you guys. What is the cardinality of v omega plus n? I mean, what we did, there is something not completely right in what we do, what we just did, but we'll get into that in a minute. Let's look at this. Well, so let's start with cardinality of v0, of v omega. V omega. Well, V omega is a union of finite sets, a countable union of finite sets, right? Each of these Vn's is finite, has size 2 to the 2 to the 2 to the 2 n times, and there, but it's still finite, and you say countable union of finite sets, this is countable. So countable means it has cardinality, aleph naught. Aleph naught means countable. And then we're starting taking the power sets, right? So then cardinality of v omega plus 1 is 2 to the aleph naught, which is cardinality of the reals. And then we took the power set. So then we get that the cardinality of v omega plus n is 2 to the 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 aleph naught. And then this chain has n many 2's. So it's a pretty large set, right, that we get up there. So do you guys see what, when I said that there's something fishy up here, what is that fishy up here? Well, first, let's see if we are defining this according to the recursion, transfinite recursion principle in the right way. Well, we are, right? So we are essentially taking, I mean, we are using the previous values of the value of the function v to define the new value, right? So that's just fine. So here, the function g that we need, this function g, what is it? G of a function h, where h is kind of the restriction of v up to segment of t, is equal to the union of h of power set of h of t, h of b for b in the domain of h. So if you apply this h, we get exactly what we want, right? We get that vt is equal to g applied to v up to the segment of t. Correct? So then this is, the definition is by recursion. Then the issue here is, so I move this to the corner so we can work up here. So the issue here is this function g, where does it go to? How can we define this function g? Because this function g is taking, like, these images are the power sets of the power set. So g is supposed to go, according to our transfinite recursion theorem, g goes from some set b to the less than a to b, right? And then when you iterate, you end up with this function v. But what is b here? B is like, I don't know what the b should be here, no? Like, I mean, the image of our function v is going to be all these bigger and bigger sets with larger and larger cardinality. Where are we getting this function g from? Because we need to define g before define f. Let's take a look back. In the transfinite recursion principle, we are given a function g, and then we obtain our function f using it. But we have to be given this function g, and then if we have the function, we have the range. But then here we will have that all these guys, v omega plus n, for n in the natural numbers, this is going to be inside the range, right? This is a subset of the range of the v that we're going to be able to define. So it should be a subset of b. But we don't have these guys. We have each of these guys separately, right? We can build v. If you give me n17, I can apply the power set axiom 17 times and build v omega plus 17. Fine. N equals 174. I can define v omega plus 174. But how do we put them all together in a set? Like this set up here. How do we build this set up here? We need to build this set before we define the v's actually, because we need to have this function g, right? And so far the axioms that we have do not allow us to do that. The axioms that we have, they only allow us to take subsets of axioms that we had before. The only way to go up is by applying the power set. So we can apply the power set once, we can apply the power set axiom twice, we can apply it, and then, but after we apply, like in this case, omega many times, how do we, I mean, we have each of these sets isolated, but how do we take the union? I mean, to take a union of a set, you first have to have them all together in a single set, right? If you want to do, for instance, that, if you want to do the union of all the v omegas plus n in the natural numbers, we need to have this set first, which contains all of them together. Where do we get this from? So the answer is that the axioms that we have so far do not give us this set, right? So if you want like cardinality up that comes after taking the limit of all these guys, so the cardinality of what we should call v omega plus omega, we need a new axiom. And the axiom that we need is called replacement. So here is the replacement axiom. So before stating the axiom, we need this definition. So suppose you're given a formula phi of first order logic in the language of set theory, and it has two variables, what is called two free variables, x and y. The formula satisfies the following. If the formula satisfies the following property, we're going to say the formula is function-like. Okay, so I'm defining this property of the formula, and the property is that for every x in A and for every y1 and y2, if phi holds of x together with y1 and phi holds together with y2, then it's because y1 and y2 were already equal to begin with. So okay, so then it's essentially this is saying that if phi of x holds with something, there is a unique something that it holds with it. So in other way, this will be the same thing as saying if there exists a y such that phi xy, then there exists a unique y such that phi xy. And that's why it's function-like, because for every x, If there exists a y, then there exists a unique y that is related to x according to this function. Okay, so this is so for instance, for example, if f is a function from, let's say, a set a to b, and we let phi of x, y be the function f of x equals y, then this formula would be function-like. Okay, it will have f as a parameter, that's fine, but it will be function-like. For each x, there will be a unique y, if there is one. So not all formulas are going to be function-likes, but some are going to be function-like. So essentially, it's a formula defining a function. The difference is that maybe we cannot define a function directly from the formula, right? A function needs to be a set, essentially, and this formula maybe doesn't define a set. It kind of behaves like a function, but it's not a set in itself. So the replacement axiom scheme says the following. It's a scheme, so for each formula we have a different instance of the replacement axiom. So we have infinitely many instances of the replacement axiom, and it says the following. So for each formula phi, if the formula is function-like, which is like this definition that we have up there, then the following holds. For every set A, there exists a B such that you belong to B if and only if there exists an X in A such that phi is Y. So essentially what it's saying is that if here you have an A, there is going to exist a set B such that something belongs to B if and only if it's related to some X in here via phi. Okay, and this phi is supposed to be function-like, so the elements here are related to different elements here. Some elements here might not be related to anybody, but every element is related to at most one thing. And then the function is telling you essentially is that this range exists. Okay, so that's kind of what replacement tells you, that this range exists. And once you have B, you can now define F to be the set of pairs A comma B that belong to A times B, such that phi A B holds. We can define now this by a subset axiom. And essentially what you have is that F is a function with domain of F as subset of A, and the range of F is actually equal to B. Yeah, so the replacement axiom implies that if you're given a formula that is function-like phi, and you want to restrict this function to a particular set A, and now A is given as a set, then you actually get a function as an object. This function f, that is essentially the one that we have here, is the function f. It exists as an object in our universe of sets, right? So the formula, like kind of like many x's get mapped to some y's, but maybe it's like all sets get mapped to things. If you restrict the domain to an actual set, something that you know is a set, replacement is telling you, well, then you actually get a function whose range is an actual set. Yeah, makes sense? So let's consider an example of this. For instance, suppose the formula phi of xy is a formula that says that y is equal to the power set of x. Okay? This is function-like because for every x there is a unique power set. So this function is function-like. but it's not a function. It doesn't give you a function because the domain will be like all sets. I mean, essentially, it's like a function whose domain is all sets, and for all sets, it gives you an image, the power set. But yeah, we cannot have the domain to be all sets because all sets is not a set. So itself is not a function, but we can restrict it to a fixed set. So if you I don't know, take a set B, what this does is that we take a set A, and what the replacement tells us is that there is a B, which is an actual set, which is essentially the set of all the power set of all x for x in A. Alright? So that is something we couldn't do before, because before we didn't know. I mean, if we wanted to do this, use this axiom, we need to say, well, where are we taking these guys from to use the subset axiom? So we cannot do this using the subset axiom because where are we taking all these power sets from before we have them? I mean, I guess in this case we could have, because it's the power set. In this case, we could have figured it out in some other way, in this particular case. But so the replacement axiom tells us in situations like this, when you have a function like thing, you don't need to apply the subset axiom. You can get it directly. So you get that this B exists, and then we can define this function of all the that maps A to the power set, but only for the little a's that belong to capital A, right? So essentially the restriction of phi of this function-like formula to A, it is a function. So it is a function. And this one has domain A and range B. So going back to this case, when we have all these v omega plus 1, v omega plus 2, all of these, it takes a little bit of work, but you can define a function phi n comma, let's say w, that holds if and only if w is v omega plus n. So essentially, if w is the power set of the power set of the power set of the omega n times. It's not immediate how you find this formula phi, but okay, you can define it, and we're gonna see that in the next video. And once you have this, what replacement is doing is telling us that the image of omega. So first we can show that for every n there exists a unique w, namely v omega plus n, such that phi n w, and that unique w is v omega plus n. So once you have that, you get that this formula is function-like, and you can take the image of omega. So by replacement, there exists a set B, which such that for every n, there exists the set V omega plus n, which is the image, belongs to B. Alright, so essentially we get this setup here. So replacement gives us this set. So of all these guys. Yeah. Again, there is a bit of a technicality here to prove this thing that we need to do. So once you have this B, then you can keep on going, right? Then you can take the union of all these guys, and then you can consider V omega plus omega to be the union of V omega plus n for n in the natural numbers. And this one is going to have cardinality 2 to the 2 to the limit of this 2 to the 2 to the 2 to the f naught at the end, and you can keep on going. Then you can do V omega plus 1 to be the power set of V omega plus omega, and then all the way, and then V omega plus omega plus omega to be the union of V omega plus n for n in the natural numbers, which again you need to use replacement to get this very large set. But yes, and then you can even keep on going. V omega times omega down there, and you can keep on going. We'll get to that later. See you guys in the next video.